Okay, let's talk about strategy. As a cognitive neuroscientist studying language, I'm essentially using a human brain to understand human brains. Now, given all the advances that we've seen in neuroscience over the last couple of decades, it's easy to lose track of just how much the odds are stacked against us. Okay? So, your brain is depending on someplace between 1 and 5 trillion synapses to do its work. Okay, for a little perspective, 5 trillion seconds is a little bit over 157,000 years. You can probably do that in your head already. And so what we're essentially trying to do is we're trying to figure out how a machine with 5 trillion working parts works using a mind that cognitive psychologists tell us can hold, oops, a little ahead of myself. The cognitive psychologists tell us can only hold on to 3 to 7 bits of information at a time. The odds are stacked against us. This is not the way we want to start. So our strategy for dealing with this sort of situation is usually divide and conquer. We take this big, overwhelming problem and we cut it up into small, bite-sized pieces and understand it a little bit at a time. It's a good strategy, but there are 2 challenges that go along with this. The one challenge is that if we take the thing apart, we ought to put it back together again. Okay, so divide and conquer is a good first step, but we also need to integrate and appreciate as a second step. The other problem is we want to make sure that when we're chopping it down to little pieces, that the pieces aren't too small, too artificial, too decontextualized to be meaningful. So you have to go where the action is. And with brains, the action is in motion. So if you've ever tried to meditate and failed, I'm assuming that's most of us, if you've ever tried to meditate and failed, you know exactly what I mean. Okay? If you want to capture the brain at work, okay, you don't need this kind of complexity. You need this kind of complexity. Because brain processing is high-speed fluid improvisation with transient, self-organized networks flying together into virtual machines, assembling a bunch of different analyses, doing their job, fading away, and then being reconfigured into the next machine to solve the next problem. Okay, I want you to imagine flash mobs erupting into highly choreographed performances in the chaos of a crowd leaving Fenway Park after a game. They stand up, they do their thing, they disappear, we move on. Okay? If you want to understand how brain solves a problem like understanding speech, you need to tackle that kind of complexity. Okay? Here's how we do it. Instead of using pictures, we use movies. Okay? So what we do is we combine 3 different kinds of brain imaging to make high-speed movies of the brain as it solves problems. So what you're seeing here is about a half second of processing of a brain listening to the sentence ba, or the syllable ba. Now the richness of these data allows us to do a couple things. First, we can use a technique called neural decoding that allows us to look at activity in one chunk of brain and see what kind of distinctions it cares about. Does it care about whether it's hearing a P versus a B, a noun versus a verb, or maybe someone with a Boston accent versus a French accent? The other thing that we can do is we can see how these decoded regions talk to each other over time. Okay, this is called effective connectivity analysis, and what I want you to notice is just how complicated this is. This is a basket full of over-caffeinated snakes here. So you're going to have a hard time making sense of this. Your palms should be getting sweaty just thinking about this kind of complexity. Now I want you to listen very carefully. The sound system is not on my side for this.
It's hard to recognize speech.
Did you guys hear that? Okay, I apologize. You'll get to hear it again in a moment. Anybody here think that they understood it? Okay, let me go on. So here's the deal with this. Aside from the sound system problem, in order to understand what this guy just said, you have to take a couple things into account. You have to take into account the fact that he is male, he has a Finnish accent, 10 seconds. He's speaking at a moderate speed, he's trying to make sense, okay? And everything's supposed to be on context. Here's what it sounds like together.
Stormed the coastline pretty hard. I think the waterfront will be covered though. It's hard to recognize speech.
Okay, so I'm just going to show you very quickly what we're doing with all this. We developed a technique called effect-tone mapping. What we do is we look at all the different factors that could influence how you understand speech, look at the patterns of interaction that we see for each of them, and then use machine learning to figure out what is essential about those patterns. Then what we do is we put people in realistic situations where there's a lot going on, and then we use machine learning to take them apart. Basically, we can see how all these different pieces, which we've taken apart in the lab, work in the real world together. Okay? And the result is we end up with meaningfully complex, integrated understanding. And the punchline, I think, is that the brain may not be able to understand itself, but the right kind of data and a little machine learning can help even the odds. Thank you.
Thanks, David. Okay, let's see. Who did I start with last time? Christine, let's start with you.
Oh, no.
Oh, no. I'm sorry.
I loved the beginning question, or the beginning statement of how do you understand kind of that 5 trillion going down to 3 to 7 chunks at a time, right? It just captures the complexity of that brain research. And I love the kind of juxtaposition then with the ending of, and the brain can't even understand itself, right? So it talks about the complexity. There's a lot of metaphor in there, some of which I really enjoyed. The flash mob I actually got confused by. I thought the map showing kind of this versus understanding the movement, that really helped me to understand how you're tackling the problem. For some reason, the flash mob analogy.
I was trying to find 2,000 volunteers to film it, but I couldn't get them together.
Just, I was at 3 to 7 chunks. I wasn't able to quite understand that first part. So I thought you did a really good job of kind of describing the problem and why AI is needed, which I felt was strongest here. And of getting us to really understand the complexity of it. There's just a little pieces in the middle where I could have used a little more clarity.
Karen.
So I deeply disagree with my infinitely esteemed colleague. And I loved the flash mob. And in fact, I thought that you could even start with something like, I'm about to overturn your idea of the brain. Everybody thinks of it as this phrenologist map, right, where you have different parts of it that do different things. Well, in fact, all it ever is flash mobs. I mean, it's a combination probably, but you're having constant flash mobs. It's always in motion. Different parts are doing different things. And so that made my brain kind of light up. It felt really good to have that, my head twisted around like that. And then you lost me toward the end. Like, I felt like, I think he's saying something about how even very simple speech sounds unleash all kinds of incredible complexity in our brains, and therefore we need to use AI or machine learning to what? And then I was lost. So it petered out at the end, but I would love to see your next iteration, so I can and great humor all the way through.
Yeah. Rich.
Yeah, so ditto the humor. I really think my favorite line was the basket of over-caffeinated snakes.
Yeah.
Wow, that's excellent. That's great. My suggestion would actually be, and I know, like, first of all, how hard is it to give a 4-minute presentation around something so complicated? It's like a challenge. And it's an extra challenge when you've got a device that you're not really sure it's going to work or not, so you're using a different computer. So, I mean, I know what you're going through with that. And I would love for you to be able to get out from behind the lectern a little bit.
Yeah, I couldn't because there was no.
Right, exactly. I know. So I know that was a limitation, but it's just so great when you can, the crowd can see you, and you really can connect with them one-on-one, so you can make some more eye contact with folks. You can get some of that more personal connection, because that's really important that they get that emotion from you as well about, we got some of it, but I'd love for you to get even more.
I'm huge, slow-moving, and highly reflective. So
Yeah. So anyway, yeah.
I really liked I think it was the first maybe 30 seconds or so, 45 seconds, where you had that question, how can we use the brain to study the brain, and then brought up the 2 big challenges of dividing and conquering doesn't necessarily allow you to build it back up, and making sure that you're dividing it into manageable pieces. And then I also really liked where I think you were going at the end, which seemed to be sort of an example to demonstrate those. And I think that all the stuff in between that, you might have just been able to not mention, because I think you started going into a lot of details, but then because you only had a limited amount of time, you weren't able to use those details for the example. So then the details didn't really help my understanding as much as they would have if you just spent those next 4 minutes on like one example and brought in the different details as they were necessary.
Great. Thank you very much.